Welcome. Today we are going to be looking at describing the different types of radioactive decay and their strength, alpha particle, beta particle, gamma ray. We will also look at the different types of decay. Next thing we're going to be doing is solving half-life problems coming from our textbook. And lastly, explain the benefits briefly of nuclear radiation. All right, let's go ahead and get started. Again, as with any time that I have you do vocabulary, if the notes that I put up relate back to the vocabulary, I would just go back and highlight that one to know it. I just want to go through these so you don't have to double write them if you've already written them. So, radioactive decay. This deals with the spontaneous degeneration of a nucleus into a lighter nucleus. So, radioactive decay involves something like uranium breaking down. So, it'd be like uranium 230, uranium 238. Breaking down into thorium-234 or something like that. There are different types. There are different types of radioactive decay, and that's what we're going to be talking about today. Alpha decay, beta decay, gamma ray, things like that. Nuclear radiation, it has to do with the particles or electromagnetic radiation emitted from the nucleus during radioactive decay. So this is going to be, nuclear radiation is kind of like the energy that's associated with decay, radioactive decay. And the higher the energy of that particle, the higher the energy of that decay, the more likely it is to be harmful to our bodies or harmful to us. Contrary to what Hollywood and movies and TV would like you to believe, exposure to radiation does not turn you into a superhero. More than likely, it's going to cause you to develop cancer, develop other mutations that are problematic for our body. All right, so in any type of radioactive decay, it involves an unstable nucleus. Understand that everything past uranium on the periodic table, that's 92 and up, is what's called the transuranium elements. They are all unstable. They will all break down. So they will all undergo radioactive decay. And any element can be radioactive. It just depends on how the nucleus is put together, and really it kind of depends on the proportionality of protons to neutrons, things like that. The last natural element, I have to look that up. I don't know it off the top of my head. I know at some point they all become synthetic, and I can't remember right where it starts. I want to say it's 103, but I'm not sure. All of the nucleosides beyond, and nucleoside was one of your definitions from yesterday, all the nucleosides beyond atomic number 83 are unstable and thus radioactive. So it actually goes a little bit further back to bismuth being radioactive. But mostly we focus on uranium because that's probably the most famous radioactive element. That's what we use for nuclear power and all of it.
Last natural one, 43 is not natural, 61 is not natural.
Okay. So you just look that up? All right, thank you. All right. So let's kind of move forward into what we really want to get into today. All right, so the types of radioactive decay. Now, all right, so a nucleoside's type of rate type and rate of decay depends on the nucleon content and energy level of the nucleus. So first type that we're going to look at is an alpha emission or alpha decay. In that, an alpha particle is released. Now, what I really want you to know about an alpha particle is that it is essentially a helium atom with a +2 charge. All right, so it's a helium atom without electrons. So 2 protons, 2 neutrons. And so if you look at uranium has 92 protons. It spontaneously decays into thorium, and when it does that, it gives off an alpha particle. So uranium, which is at 92, decays into thorium, which is 90. There's your 2 protons. It's going to go from 238 to like 236. All right, or uranium, it might be uranium-236 that decays, and it becomes thorium-234, giving off those 2 protons and 2 neutrons, thereby deducting the whole mass by 4. And then we see that whenever we write this in nuclear notation, a alpha particle is going to be helium with a mass of 4 and a atomic number of 2. All right. So we could see it something like this. Uranium 236, and that's going to be 92. It decays into a helium or a alpha particle. That should be a 4, 2, He plus thorium 234, and that's going to be 90. All right, so this would be an alpha emission. That helium goes off, and eventually it's going to pick up some electrons, become a helium, or it will collide with another nucleus, causing a fission reaction to occur, or something like that. An alpha particle is the heaviest or the largest of all of the radioactive emissions, radioactive decays. So with that being that they're kind of heavy, they also are slow moving, so they're kind of the lowest energy. They're going to be the least penetrating of all the radioactive particles. All right, sorry. All right, so moving forward, the next type of radioactive decay is a beta emission. What I want you to know about this is a beta emission is essentially an electron that's being emitted. So as far as terms of mass, what do we know about electrons as far as their mass in relation to the whole atom? If we lose it, very small. So does it really affect the overall mass of the atom? No. Or not noticeably enough for us to even count it. It will affect the charge, though. So a beta emission, so what happens in beta emission is that basically a neutron breaks apart and it emits an electron out of it, and then that neutron becomes a proton. So essentially what you would have is if you had thorium there that's going to go through beta emission, one of its neutrons is going to convert into a proton, so the mass will stay the same because it emits an electron, so it emits a negative charged particle, and that leftover material is now a proton. So as it emits that electron, Thorium now becomes palladium. I think that's what it is. No, proactium. Um, and now we have, it changes into a different element. So all of this relates back to what the original starting of chemistry really was the pursuit of alchemy, and the pursuit of alchemy was to try to convert one element into another element. It was basic. Essentially, they were wanting to convert it into a precious, a worthless metal into a precious metal, or something like that. And it is possible to do those type of things, change one element to another. We see it all the time with radioactive decay. We see it happening naturally. The problem is, if we really wanted to convert lead into gold, the process is so expensive that it's not worthwhile to do that. So that's the thing, and that all of that process of converting one element into another is something called transmutation. That was one of your words yesterday as well. All right. So in beta emission, the atomic number is increased by 1, and the mass number stays the same. All right. Sorry, did anybody need more time on this slide? So in a beta emission reaction, you would see like carbon-14, which is what we use for radioactive dating or radiocarbon dating. Carbon-14 undergoes a beta emission, so a electron essentially is emitted out of the nucleus. So taking one of those neutrons, converting it into a proton. So we see the atomic number goes from 6 to 7. The mass stays the same because a proton and a neutron are essentially the same mass. And then this beta particle is emitted. And that beta particle is essentially an electron, a negatively charged particle with very, very low mass. When we're looking here at the beta particle, you can look at either one of these two. This 0 on the top represents the mass of that beta particle, and the number down here is telling us that it has -1 protons. So it doesn't have a proton, but it has a charge. All right. Remember, this number here is telling us number of protons, so this is still a nuclear notation, or isotope notation is another way we call that. So this is just representing that to tell us it's -1 protons, or less than 1 proton.
The difference between an alpha and a beta is just the both come from the nucleus, and then
Okay, so an alpha particle. Alpha particle is 2 protons, 2 neutrons. A beta particle is basically an electron. And then we're going to talk about some more. Now, a beta particle is really, really small. It is a high speed, but it is not the highest speed form of decay. So gamma is typically the highest speed that we associate with it, but we also have something called a positron, and
Is alpha more dangerous than beta?
no. You would prefer the alpha because it's not going to penetrate our skin. You can clean it all up. It just takes time. All right. 5, 4, 3. All right. So next type of radioactive decay is positron emission. This is probably a new one for you. I know in physical science we really only deal with alpha, beta, gamma. We don't really deal with positron. So a positron is a particle that has the same mass as an electron, but it's a positively charged particle. So remember that whenever we do a beta emission, it doesn't change the overall mass. It just emits that negative charged particle that we tend to call an electron out, and the proton number goes up by 1. So when we're looking at this, to decrease the number of protons, a proton can be converted into a neutron by emitting a positron. So in the last one, in beta, a neutron was converted into a proton, and in positron emission, a proton is converted into a neutron. And I'll write an example of these. Like I said, I don't really like writing the reactions for positron or beta. Those are the parts, whenever I had to do these in college, these were the parts that I always got wrong on the test, because I didn't like doing them. And I'm not having you write these reactions out. I'm not even having you recognize them on the test. I'm really wanting you to know more of what's happening as an overall. So the definition is more what I'm concerned with.
I just want to tell you, I have a 77% chance.
Okay.
There you go.
All right. So if you look at my example, we have potassium 38 that is going through positron emission. So notice that in this case, what I really want you to notice is how it differs from a beta emission. All right. In beta emission, the masses stayed the same, but instead of the argon is not 19. What did I write wrong? That was my fault. 18. That should be an 18. All right. So we have potassium undergoing positron emission. So we eject this positively charged particle, which we are shown right here by this symbol. It has no mass, but it has a positive charge. That, in turn, turns one of the protons in potassium into a neutron, so we maintain the same mass, but our atomic number drops by 1. All right. So this statement right here is probably the key thing to understanding positron emission. This is the statement that I am probably going to test you when it comes to it. All right. The atomic number decreases by 1. The mass number stays the same.
Even as that positron?
The next type of decay is electron capture. This is another new one that you probably haven't heard before. In electron capture, an inner orbital electron is captured by the nucleus of its own atom. So we have this atom here, and I'm going to go very, very basic and not to reality, but we have this atom here with an electron that's orbiting around in the 1s orbital. So I'm going to draw my little negative charge here. And for whatever reason, that electron is drawn into the nucleus. So what will drawing that electron into the nucleus cause to happen? What will it change? Not negative charged, but it will take one of the positively charged particles and turn it into what? Neutral. All right, so basically when this happens, an electron enters into the nucleus, causing one of the protons to become a neutron. So going back, beta emission, an electron is ejected out of there. So something goes from neutral to positive. positron emission, a positive particle is emitted out of the nucleus and something goes from positive to neutral. And then in this one is kind of the reverse of that, where a negative particle enters into it, causing something to go from positive to neutral. All right. So there's basically two different ways that you can convert a proton to a neutron. Really, environment, depending on the element and the environment. So let me go ahead and write an example of this happening. Hopefully it'll make a little more sense. All right. We have silver. And I'm going to come back and write the numbers on these in just a minute. So, all right. Now, before and that's a 47, by the way. Before I write the numbers on palladium, before I write the numbers on palladium, let's look at this. We are taking in an electron into the nucleus. So what's going to happen to this mass number up here? Is it going to change or stay the same? Stay the same. So the top number is still going to be 106. Now, we're taking in a negative charge, so what's that going to do to this number? It's going to reduce it by 1, so it'll make it a 46. So if we look at the periodic table, silver is atomic number 47, palladium is atomic number 46. So we basically transmute silver into palladium naturally. All right. So in this one, again, the statement that kind of sums it up, the atomic number decreases by 1 and the mass number stays the same. Because remember that an electron essentially has no mass in relation to the size of a proton and a neutron. So it's essentially like if you had about 300 ants crawling on your foot, when you start running away to get the ants off your foot and jumping around and all that, you don't really notice the mass of the ants. You just know they're there. All right. It might not be the best analogy, but last type of emission is a gamma emission. And so I put the electromagnetic spectrum on there because gamma rays fall on the EM spectrum. Gamma rays and X-rays. We typically associate these with the highest form of radiation or the most dangerous type of radiation. These are very high energy electromagnetic waves that are emitted from the nucleus. Now, since I'm saying a wave, all right, so electromagnetic wave, is any mass going to be associated with this? No, only energy. So if you remember when we talked about excited state and ground state in electron configurations, when an electron is moving from a ground state to an excited state or from excited state back down to ground state, how do we know that's happened? What do we see it as? When we go from ground state to excited state or excited state to ground state. Think about, not as electricity, but close. I'll give you a hint. What, right here on the graph? We see a... Yes, ma'am.
Can you send it to the front office with her book, please?
Yes, ma'am. So whenever a gamma emission occurs, we see a visible flash of light. All right. So gamma rays are high energy electromagnetic waves emitted from the nucleus as it changes from an excited state to a ground energy state. So basically, we see that flash of light and all of that. And let me write down an example of this one for you, just so you can kind of see it. If this one has one. All right. A half-life, and half-life is typically represented by time, time with the subscript of 1/2 next to it. That subscript doesn't mean anything other than just telling you that it is a half-life, or the time it takes for half of the atoms of a substance to decay. And let's just say that you start off with something that has 50 grams. After one half-life, how many grams of that substance would you have? 25. After another half-life, how many grams would you have? 12.5. And so on. Now, so when we deal with half-life in relation to grams, it's easy because it just keeps halving like that. If we're dealing with half-life in terms of atoms, you can't have half of an atom, so you would round up or round down and go from there. Yes. Go. All right. So half-life, again, is the time required for half of the atoms of a radioactive nucleoside to decay. Each radioactive nucleoside has its own half-life. So every radioactive element, every radioactive thing that we experience has its own half-life. That half-life can be anywhere from a couple of hours to thousands, if not hundreds of thousands of years. I don't know off the top of my head. Only problem is coffee is a compound, so it's not gonna. Half-life is a little different in that context. They have a shelf life. Oh, well, no, I mean that's depending on metabolism.
Will everything turn into hydrogen?
No. All right. So more stable, so basically off of this slide, I want you to know this statement and this statement. Basically, the more stable an element is, or the more stable it is, the more slowly they decay. So the longer the half-life. Shorter the half-life means very unstable. A long half-life means very stable. All right. Look at a sample problem. All right. So we have phosphorus 32, and it has a half-life of 14.3 days. We actually just saw this verified by another source in the video that we just watched, that phosphorus half-life is 14.3 days. Sorry. So how many milligrams of phosphorus 32 would remain after 57.2 days if you start with 4 milligrams of the isotope? So the first thing that we need to find out is how many half-lives have occurred. So we have 57.2 days equals 1 over 14.3 days. So 1 half-life. All right. So how many half-lives have occurred? 4. All right. Now, So in order to find out how much is left, we essentially take our 4 milligrams and multiply it by 1/2, 1/2, 1/2, and 1/2. So how much is going to be remaining? 0.25 milligrams. All right. So a 1/4 of a milligram will be remaining after 4 half-lives, or after 57.2 days. All right. Now, for our purposes, if we wouldn't do this, but let's just say that we had the sample set up somewhere where we could observe it, and this was happening. You wouldn't see the sample size get smaller, because remember, as those half-lives are going on, as it's going through its decay, it's turning into something else. So from our perspective, the pile is going to stay essentially the same size. It's just going to change from one substance to another, and as time progresses, it'll go on. That's the same thing with how they do radioactive dating and all. Living organisms do have a certain percentage of carbon-14 in their bodies, and so as things decay over time, so does the carbon-14 in the organic material. So we can take something really old and use this process to find out how old it is by looking at how many half-lives occurred and all of that. So when we know how much should be in the organism when it was alive versus however many years passed and how much is in it now. And we can see that. All right, so moving forward, that's just showing you the work that I just did, or that we just did together. They came up with the same answer we did. All right, so I don't need you to know that. That should have been deleted. All right, I do want to talk about nuclear fission and nuclear fusion. Things I want you to know about nuclear fission are those two statements. In nuclear fission, a heavy nucleus splits into more stable nuclei of intermediate mass. So I don't want to give you a real-world example, but let's just say that we have a nucleus that has a mass of 140, and something strikes it, like a neutron traveling at high speed hits it, and that causes a fracture in the nucleus. When that nucleus fractures, then let's just say that it splits into 2 different smaller nuclei, one of them being a nuclei with 80 and another being a nuclei with 60. It could be 70 and 70. I just showed it like that. Now, when it does that, other things are released. Sometimes, let's just say this was 78 and 80, and 78 and 60, and then that also means that maybe two other neutrons were emitted too that can go and split other things. So, as the fission process goes on, the neutrons that are emitted during this process can cause other nuclei to split as well. So again, putting it into an example, it's kind of like bowling. When the bowling ball hits the pins, the other pins hit other pins, and it causes this big chain reaction. Same thing inside of nuclear reaction. We can have this happen. The key for us, the reason why fission is such an important deal for us, is we have an enormous amount of energy that's produced. We see it in 2 different ways. One way is if we have an uncontrolled chain reaction, we kind of basically look at that as what a nuclear warhead or a nuclear bomb is where we see this big explosion. That's just all of that heat energy being released in it, and it actually has to do with air pressure. Lower to the ground, the air pressure is high. As you go up, the air pressure is less, so it spreads out when it gets up. Um, so the thing that I want you to know with this, a controlled nuclear fission reaction is what we do to produce nuclear power at the power plants and things like that. Typically, we have these control rods made out of a certain radioactive element. We bombard them with neutrons, causing them to start to fizz or start to break. And we allow that reaction to go on for as long as it's in a controlled amount. If for some reason the reaction starts going out of control, all of this happens inside of a large pool of water. And if the reaction starts going out of control, they pull the fuel source out of the water, and then the reaction stops. It slows down until it eventually stops. It's a very, very, very good process. However, there are problems that happen from time to time. For example, the one in Japan where the earthquake occurred and basically caused the reactor to crack, and they had to abandon it before they could remove the control rods, and you had leakage of the heavy water, the radioactive water, into the environment. Other ones.
That when we bomb them, their shadows are still in them. Guys, quiet down.
This is just kind of a picture of what's happening in fission. So you can see this neutron being fired at a uranium atom. It splits into krypton and barium. Yeah, krypton and barium. And then as that happens, more neutrons are released. It hits more uraniums, causing them to split into other items or other atoms. As we see, it doesn't always end up being the same things. And it keeps happening until we remove the fuel source. So once we remove the uranium, there's nothing else left to fizz. So it stops. All right. So this is the next thing I want you to write. Make sure you know the definition of nuclear fusion. Again, nuclear fusion, we have two nuclei of lower mass that combine to form a heavier, more stable nuclei. So, going back to the Spider-Man movies and all of that, Doc Ock tries to make a fusion reactor with tritium, which is essentially, that is a hydrogen that has an atomic mass of 3. So it has hydrogen always has an atomic number of 1, so it has 1 proton and 2 neutrons. And so that hydrogen will combine with another hydrogen, and then after the reaction happens, we end up with helium, which is 4 and 2. So 2, 6, plus 2, and that's not nitrogen, that's 2 NEU, 2 neutrons that are released. All right, and those 2 neutrons are what's associated with the energy that's involved in it. And when this happens, tons of energy is released. Now, herein lies the problem and the and the attraction to fusion. If fusion reactions could be controlled, basically we would have an unlimited energy source till the end of the foreseeable future. The problem is that fusion reactions require a great deal of heat and pressure, and as it stands right now, we don't know how we could cause a controlled fusion reaction to happen and contain it. We can't contain it. We can
We can blow stuff up with it.
Yeah.
Pretty good at that.
So you know, they are seeking ways, and you might hear terms thrown out like cold fusion and all of that, which is essentially a fusion reaction that happens at a low enough temperature that you can contain the energy created. Essentially, the only way that you could probably do it, and I don't know enough on this subject to really speak on it, but you would have to find a way to remove the energy being produced as soon as it happens so that the overall reaction doesn't heat up. All right. And then the last slide is just some applications of nuclear radiation. So a couple of ways that we use radiation, nuclear radiation, is radioactive nucleosides in medicine. So we do use radiation treatment for things like cancer and all that because it can be used to kill cells, including bad cells like cancer cells, if it's directed to a very small area. We also, from time to time, we have to inject things into the body to be able to track the flow of something. So they use radioactive tracers in that way. Also have used radioactive tracers to trace the way plants and trees communicate with each other through their root systems. Pretty interesting study that I read when I was in college about that. Originally they didn't think they did, but they found out that certain tree systems and all of that do basically send information to each other through chemicals. Not necessarily talk, but they share resources. So they basically and it's much more complicated than what it sounds like with me telling you. But basically, they injected this radioactive substance in one tree, and then eventually found it in trees that were miles away from it.